So let me kind of, since it's now 2 weeks ago, kind of give a little bit of a reminder. So we were looking at these four objects. On the one hand, we had an ensemble of time-independent and divergence-free drift. So that was a Pickley number epsilon times the projection onto scales which are larger than 1. So there was a UV cutoff scale which I set to 1. Then of course the projection onto divergence-free vector fields, and this was applied to spatial white noise. And what we were interested in is the a solution of the corresponding parabolic or semi-group version of the drift-diffusion equation. So minus Laplacian plus b grad u is equal to 0 with initial data which are given by the identity. So in a certain sense, you may interpret this u as the expected position of a particle which undergoes drift diffusion and which started at position x at time 0. And so in a certain sense, that's kind of a PDE with random coefficients. And I'm making a connection to diffusion on the Lie group of SL2. So first, for this purpose, I said that there is distinguished Brownian motion on the Lie algebra SL2, so of trace free 2x2 matrices. And it's distinguished by saying that it's SO2 invariant. It has the property that if you take the expectation of B square, so B is a matrix, B square is again a matrix, then this vanishes. That's important for having Ito equal to Stratonovich. And then there was a normalization, which was that the matrix which you obtain by another multiplication, B transpose B, that this is normalized to be the identity. And that uniquely determines this Brownian motion. And then we were interested in something which you might call a diffusion on the corresponding Lie group, SL2, which I defined with kind of a variable starting time t tau. So I'm starting at time tau star, and I'm solving this Stratonovich equation for tau larger than the starting time. I think I put the star downstairs most of the time. And here it doesn't actually matter whether I put Stratonovich or I put Ito because of this condition, as I tried to explain a couple of weeks ago. And then we start at the identity, meaning for tau less than tau star, I set this matrix to be identity. So this is nothing else than the than really kind of the diffusion on this Lie group, which is generated by this Brownian motion on the Lie algebra. And then the main result with Peter Morphy and Christian Wagner from this year was that there is a kind of relationship between these two objects. So there exists a coupling, and I, in a certain sense, explained last time what the coupling is between the spatial or environmental noise and this dynamic or time-dependent, tau-dependent noise, such that for any time horizons t and any points x, if we look at the increment of the solution, let's say around the origin, we can compare it to this matrix F. Rather, it's transposed with a starting time which depends on the distance between x and 0, and a terminal time, which I'm going to explain in a second. And so this almost looks like a Taylor remainder, but it's not quite. So let's take divided by x squared. Let's take the average over our time horizon, and then the expectation. Then the result was that this is less than epsilon squared times the expectation of this object if I start at 0. And tau was a function which I motivated at the first time around, which is kind of doubly logarithmic. It's the logarithm of the square root of 1 plus epsilon squared over 2 logarithm of 1 plus s. So that was the core result from which we then derived intermittent. So in a certain sense, what's interesting about this is that this side we know pretty explicitly, although not completely. In particular, this process here is strongly intermittent because it's kind of a stochastic exponential, and so means and expectations are very different. And by this result, this intermittency transmits to the solution of this PDE, in the sense that we saw that if we were looking at kind of modulus of continuities, spatial modulus of continuities of this equation, we got essentially a log Lipschitz, a Lipschitz behavior modular log, and the powers of the log depend on which moments you're considering here. I mean, you get a different answer for 2 and something that's larger than second moments. And so that's perhaps the interest of connecting these two sides. Also, I think what's interesting is that this is an environmental noise, and this statement tells you that this the effect of this environmental noise, of this frozen-in spatial noise, can be captured in a certain sense by dynamical noise, by kind of a Langevin type of noise. Okay, so that's roughly speaking what we did, and already last time I told you that this essentially relies on what you may call scale by scale or incremental homogenization. And that's, again, repeating a little bit what I said the last session. So, so the idea is to introduce some artificial, so we have this hardwired small-scale cutoff. Now let's introduce kind of a flexible artificial large-scale cutoff. So let's project B onto scales which are less than some L. L is a number between 1 and infinity. And again, the most convenient is to do that on the level of the Fourier transform. So the Fourier transform of BKL is just L times K larger than 1 times the Fourier transform of B. So the picture you should have in mind is that we're now in Fourier space, in frequency space, in wave number space, we're now in this interval where we anyway always cut away, in order to make this problem well posed in the first place, we cut away the small scales, the large k's, but now we also cut away the very small k's, so the large scales, and of course now we want to kind of propagate information towards the large scales, and the way we did that, and I tried to motivate that last time, is that we solve an Ito evolution for something which might be seen as a approximate corrector. And that e to evolution is given by, so proxy corrector is something which goes with a tilde and which depends on the cutoff, the artificial cutoff scale L, and has components 1 and 2. And the Ito equation was that d phi tilde is equal to 1 plus phi L tilde j dj d phi with trivial initial data. So the L equal to 1, I start at 0. And this driver is given by minus lambda L tilde d, Laplacian of d phi is equal to dB. And dB is the L derivative, so that's kind of the stochastic analysis way of writing the L derivative of BL with respect to the cutoff. So that's the that's the definition of that object. And then we consider the approximate harmonic coordinates, which are given in the usual sense. You take the affine coordinates and you add to it this proxy corrector. And then the statement was that, and that was from the earlier work with Georgiana Schatzi-Georgi, Peter Morphy, and Lihan Wang, which now got accepted by Annals of Probability, that if t is equal to L squared minus 1, so if you couple the cutoff scale L to the time horizon t in the usual parabolic way, and you choose lambda L tilde, your good guess for the effective diffusivity to be equal to lambda of L squared minus 1, which was defined previously, but let me make it explicit. So that's 1 plus epsilon square times the logarithm of L and the square root of this expression. Then the gradient of the solution to the parabolic equation, let's say at one point, let's take the origin, that doesn't matter here, minus the gradient of this proxy harmonic coordinates, again at the origin, time averaged over our usual thing here, is less than up to some universal constant epsilon square times lambda of t. And perhaps I should recall the definition. Lambda of s was defined like tau of s without the logarithm. Okay, so that's really the this type of this result is really at the core of this result. You can, in a certain sense, already see why once you have this, you're not so far from this result. And the reason is that if you hit this equation with the gradient and you insert this definition, you get something which already pretty much looks like this equation. So more precisely, what you get is gradient du tilde is equal to gradient, let me write it like this, d gradient u tilde, and L is gradient u tilde d gradient phi plus a lower order term, something which you have to show is lower order, which arises if the gradient falls onto the driver. J dj gradient d phi. So if you neglect this one, then you see that this type of equation, again I can erase the Stratonovich here, this type of equation arises provided we can identify this expression here with a Brownian motion on the Lie group, on the Lie algebra. That looks promising because it's trace-free, because B is divergence-free, and which is something which you learn from this equation. But then you have to actually check that after some time rescaling, which essentially is given by this identity here, you can pass from this statement to this statement, first on the level of the gradient, and then there is a bit more of a kind of finer argument to go from the gradient to the increments. Okay, so that's perhaps the most, the core technical result, and that's what I want to explain now in the yeah.
Why the neglected one is negligible?
So perhaps that comes that will become clearer in perhaps a little bit clearer in after what I'm doing here. So in principle, you would say, okay, so you are in a kind of in a situation where so this thing here exclusively has scales of order L, and this here, morally speaking, has all the previous scales up to L, including to L. So it's, if you put the gradient on, I mean, this is obviously Leibniz rule. And if you distribute the gradient on these two things, if the gradient hits this term, you expect that term to be smaller, because that's the larger scales. But in fact, it's only smaller by, everything happens on kind of on a logarithmic scale. It's only smaller by logarithmic scale. And that has to do with the estimates which, if I get there, one has on this object in the end. But morally speaking, it's perhaps not so surprising that kind of d phi lives exactly at the scale, because I'm doing this sharp cutoff in Fourier space, and phi tilde kind of integrates over all the previous scales. It's, I mean, you have to show it, and you have to show that it's not, not exclusively dominated by the large scales, and it's only, slightly discounted by logarithmic term in L. And so it's not obvious, but that's perhaps the intuition. Okay, so now let me try to explain a bit what goes into this, and that will be again a little bit the motivation of what I wrote down here. So that's the last section. So let me call it stochastic homogenization by Ito calculus, which is a bit in L, which is a bit weird, but it works because we're in this borderline situation. So let me start out with something elementary. So since our field B is divergence-free, of course, we can write it with help of a potential. So in 2 dimensions, a stream function, but let me be a bit more, that's notationally more convenient, do the general dimension and think about kind of a potential. So since it's divergence-free, there exists kind of a skew tensor field sigma, no, let me call it psi L, because that makes us think about the stream function such that BL can be written as the divergence of the skew vector field. In 2 dimensions, the rotated gradient of yeah, I mean, so I'm thinking of, so in my notation, this here really is, you should think of this as, now, in fact, now it's good that in one's mind one keeps tangent vectors and cotangent vectors separate. So this should be thought of almost like an exterior derivative. So that's just saying that you have a 2 form of which, or d minus 1 form, d minus 2 form of which once you take the exterior derivative. But in the 3D notation would be curl, and psi would be kind of a vector field. In 2D it's just a stream function. But let me stick here to my general notation. So that's not mysterious. And so one very convenient aspect of this is, and that's a trick which is well known, that the generator, which is this object, and if I put the subscript L, then I put the L here. So the generator can be written as a pure second order divergence form equation operator where A of L is, well, the identity matrix, but so I said I wanted to be a bit careful with respect to tensors. So it's really the kind of these standard symmetric tensor plus a skew symmetric part which comes from the drift. So you can hide a divergence-free drift in a diffusion matrix at the expense of making the diffusion matrix non-symmetric. And but then we're in a certain sense in the realm of second order elliptic equations in divergence form, and homogenization means essentially finding a pair of a corrector and a flux corrector. And one way of of writing this is you take your coefficient field, you apply it to a gradient, which is given by a constant plus kind of a perturbation, which is the corrector, and you want to connect that to a homogeneous coefficient field. Let me call it E bar, EI. That's now a cotangent vector, so therefore I put the indices upstairs, plus, again, the exterior derivative of something skew. So this is skew. This is homogeneous. So by which I mean it's both deterministic and constant. And if you look at this equation, what this really means is that this is a kind of Helmholtz decomposition in the geometry defined by this coefficient field. Because you take, you in a certain sense write this here, the coefficient field applied to gradient as something divergence-free. So this is automatically divergence-free, as we've seen here. So that's an equivalence plus plus something constant. And homogenization really essentially amounts to constructing these two objects. So now the idea, which I already explained last time a little bit, is to get a hold of these two objects, not exactly, but by writing down proxies. One is already on the blackboard, but we also need a proxy for this, what's called the flux corrector. So this is f I sigma I, so scalar is q. By hitting this equation with the derivative with respect to the cutoff scale. And if you do that, by Ito calculus, you get one term more than kind of the standard Leibniz rule suggests. So it's a kind of Ito Leibniz rule. So you get DAL. So that's the increment in L. And if I take the increment, I drop the subscript L. EI plus gradient phi IL. That's the first term on the left-hand side. And then we have AL gradient d phi Li. But then we get a quadratic variation of A and the gradient of phi Li. So this is a quadratic variation. And it is, again, a homogeneous expression. So it's deterministic and constant in space. So that's the left-hand side. And the right-hand side is simple. So we get the L derivative of what should be the homogenized coefficient plus the L derivative of the increment of the flux corrector. And now we do two approximations. I already talked about those approximations at the very first day, I guess, or perhaps the second. So we do a linearization by neglecting this term, and we do a homogenization by replacing this by its homogenized version. So again, we do homogenization, so linearization, and homogenization, which gives us dA EI plus AL bar gradient d phi I plus dA grad phi I. And I'm just copying all the rest. Okay, so those are two kind of, at this stage, completely uncontrolled approximations, linearizing and homogenizing. And now the kind of the benefit is that we get something simple, and in fact we can rewrite this identity by splitting in terms of expectations and the remainder, so let me call them fluctuations. And if we do this, we get two two identities. So on the level of the expectation, we learn that the derivative of our constant coefficient in terms of the cutoff parameter should be given by this quadratic variation, and the rest is what the remaining identity kind of vanishing expectations expressions, which are these ones. So again, you, in a certain sense, recognize a Helmholtz decomposition here, since this is, of course, still skew. This is a gradient, but now it's a constant coefficient Helmholtz projection or decomposition. And now this, in principle, can be solved by hand. So by isotropy, you know ahead of time that whatever AL bar is, it must be isotropic, so of the form lambda L times the standard tensor or the inner product. And then you, from this ansatz, which you plug in here, you can come up, you can compute this, this quadratic variation, and you find an ODE for lambda, which is d lambda is equal to, let me not make a mistake with the coefficients. Oh, I didn't write it down, but essentially it's I think 1 over lambda L epsilon square d logarithm of epsilon square d logarithm of L, which then you can solve, and you find exactly kind of this expression here. So far so good. That was kind of a very convenient simplification, but completely uncontrolled. And in fact, as I guess I mentioned already one of the last times, it's not enough on the level of the gradients. And this made us kind of work with this two-scale expansion. So I'm essentially repeating what I wrote down here, but in this slightly expanded way, where we also look at the flux corrector sigma. So this approximation is too rough or too rough for gradients. And instead, we have to upgrade it by the two-scale expansion. Let's call it the two-scale expansion, which is, we're a bit more careful on the homogenization side by saying that we take our simple-minded answer, which was d phi I, but then we hit it with what's called the two-scale expansion, which is phi L j tilde dj, and I'm using Einstein's summation convention here, and that defines an Ito evolution equation for this phi tilde quantity. And with zero initial data. So that's already what kind of was on the blackboard and what, in a sense, gives the final result. But we need something similar for the flux corrector. And that's slightly more subtle. And that, in fact, took us quite a while to find the right expression. So the way you do it is, so again, you take essentially, like here, you take sigma I close to sigma tilde I, that's the one. Here you do the same thing. Then you do a very similar correction, but where you replace this by the sigma L tilde j, dj d phi I. But then you need two more corrections, minus phi L tilde I dA, and kind of a non-martingale term, phi L tilde j, d dj phi I a. That's again one of these quadratic variations. And so we should make sure, and of course, kind of trivial initial data. So initial always is kind of this temporal language for something which really kind of this cut-off length scale. So we should make sure that kind of skewness is preserved. Because we want this skewness of sigma or sigma tilde, because otherwise we wouldn't have a Helmholtz decomposition. So okay, this sigma, the driver, is skew by definition, so we're fine here. That's a propagation term if this is just a scalar, and that's skew, so we're fine here. And now when it comes to the increment of dA, that's just it's only just the skew symmetric part that changes. So that's equal to d psi, which is q, and then again I multiply it with a scalar, so that's fine too. And the same applies here. So A, since I'm taking this quadratic variation, only the increments matter. The increments are skew. That's just a scalar, so I'm also fine here. So this expression does preserve the fact that it's skew. And now, so what did we do? We did at first a very rough thing where we linearized and homogenized, at least in the scale-by-scale fashion, which gave us already kind of some information. And then we upgraded this in this more nonlinear way, which in the end, really this product here is behind the stochastic exponential. So this upgrade is crucial for everything we found. And but now we have to get back to the question: how well are we doing in terms of this? How well are we doing in terms of this Helmholtz decomposition, which we wanted to achieve, because that's the main issue. So we monitor the error for our proxy objects, proxy corrector, phi tilde, and proxy flux corrector. Sigma tilde in the Helmholtz, in the A-L Helmholtz decomposition. Just by introducing a residuum. Let's call it FL. So in other words, I define FL by exactly this identity here, just replacing the quantities without the tilde, which I don't really have. I mean, I just have the drivers. That's a bit of a kind of a notational abuse. So now what I really just have are kind of the tilde quantities. And now I have the error. And now clearly the main task is to estimate this error.
RL as computed in the previous,
Yeah. So that's absolutely explicit. That's absolutely explicit, and these two objects are defined in a certain sense, starting from the same very hands-on explicit calculation, but then upgrading it with this by the two-scale expansion, making it more nonlinear. Yeah, and that's in a certain sense the definition of FL. So now the main task is to estimate FL. And now, and this is why, in a certain sense, it's really doing homogenization by Ito calculus. One can convince oneself that the FL itself satisfies an Ito evolution. dfl is equal to fl matrix multiplied with this matrix here, which comes from the driver. And then there are two terms which kind of feed into. And one is an expression we know, we often see in homogenization. So that's phi tilde j L A L minus sigma tilde J L gradient dj d phi. So that's the price we have to pay for committing this crime here. So that's the homogenization error. Well, it comes from the homogenization error. And then there is also a price we have to pay for doing this linearization. And now again, in my vectorial notation, I have to be careful of the order. So minus phi L tilde tensor dB. So that's the linearization error. And of course, we know that initially this error is equal to 0. So I mean, in a certain sense, that you get these type of expressions is perhaps, in particular, this one is not so surprising for people who have done homogenization. Now, of course, the way it feeds in here is via this linear term, which again is this kind of matrix iteration, which drives everything. But clearly now we can really just use stochastic analysis to estimate kind of the size of this FL. So that's the second lemma. And the first part of it answers a little bit what Peter asked. So for tau equal to the logarithm of lambda, which is double logarithmic expression in L. For instance, we get a very clean deterministic differential inequality identity for, let's say, the second moments of this proxy corrector in terms of these time variables, which I already introduced before, which kind of have to do with the stochastic exponential. And this is equal to L square d tau, from which we, for instance, get the estimate that this second order corrector is estimated by epsilon L divided by lambda L squared. And now let me for a moment come back to what I said in answering Peter's question. So in stochastic homogenization, those who have, or in homogenization in general, periodic or stochastic or any, in principle what you want is that your corrector grows sublinearly. If you don't have that, you know little. So here, sublinearity in a certain sense means that this thing grows less than L squared. But as you can see, to leading order in L, it does grow like L squared. It's just by logarithm in L that it's a little bit slower. So you're really working on this thin line between with logarithms. And so the sigma, the definition of which is a bit more complicated. nevertheless, you get something fairly explicit too. Just plus a couple of more terms, and you learn that this object behaves like this with a square here. And in fact, there is no intermittency here. I could put any exponent here, and I would still get the same thing here. So there's no intermittent behavior on the level of the correctors themselves. It's just on the level of gradients that you see intermittency. So this looks substantially worse, but in fact, if you look at how sigma tilde and phi tilde appears in the equation, then you have to be much more careful with phi tilde because it multiplies AL, and AL essentially is dominated by, at least in terms of its size, by the skew-symmetric part, and the skew-symmetric part grows logarithmically. So it's good that, perhaps it's not so surprising that we get a better estimate, or we need a better estimate on the phi tilde than we needed on the sigma tilde, because the phi tilde gets multiplied with the coefficient field itself. So, and then, so that doesn't fit here. So when you equip with these estimates, you can tackle the estimate for f. Again, you get this kind of linear term, which will eventually lead to an exponential growth in this tau variable, which is this doubly logarithmic variable in L. And the right-hand side is estimated and whereas in these two estimates, when you estimate the corrector itself, but it's really just in a certain sense ODE theory, this term doesn't matter so much or doesn't hurt you in the sense that you get the same estimate for all p because everything is driven by the right-hand side. This is no longer the case for the equation for f, because you're kind of multiplying, you have a 1 over L square in front of this, so that this here, roughly speaking, is no longer polynomial in L, but just depends on lambda L. Same applies here. So that now, for this equation, all the terms are in balance. And therefore, for this equation, as we know in hindsight, kind of estimating, pth moments would give you a different behavior. So this equation, in a certain sense, is here. For this equation, it's essentially always the largest scales that contribute, but still they get a bit discounted. For this equation, all scales equally contribute because all terms, in a certain sense, are in balance. And so that's the most subtle estimate, which gives you that. This quantity is estimated by epsilon squared times lambda L. Lambda L, sometimes I call it lambda L, sometimes I call it lambda L tilde. Let me be consistent, but it's always this thing which I defined before. Okay, so, and that's good because we now have a kind of, in a certain sense, a good noise to signal ratio. Because if you look again at this Helmholtz equation here, AL, so let me write it as 1 plus psi L times EI plus nabla phi I tilde is equal to AL EI plus sigma Li plus F Li. So why am I saying that we're happy with this estimate, or this estimate carries information? So this tells you that this quantity here is of the order of epsilon times square root of lambda L. This here, in fact, is of the order of square root of lambda L. That's essentially because the second moment of this quantity here behaves like the homogenized coefficient. But this here is of the order of epsilon times lambda L. So, so at least when this kind of skew-symmetric term falls onto this gradient term, you get something which potentially could be a logarithm to the power 3 over 4, but the error term is much smaller. So this is really kind of kind of a good noise to signal ratio, and it's essentially that equation plus an energy estimate on the level of the parabolic equation that leads to the second theorem for the homogenization result. Okay, so I think that's kind of all the details. Anyway, my time's over. That's all the details I wanted to give. Let me perhaps wrap up. We made this connection between environmental noise and, in a certain sense, fake temporal noise. But this temporal noise, kind of the driver of this natural diffusion on SL2, really arises from introducing this artificial large-scale cutoff scale into the problem and thinking of this scale as being a temporal quantity, and then using kind of an Ito equation to construct the field. And I think, that's an idea which also, for instance, comes up in kind of more traditional field theories. So as you know, the work which I know by Gubinelli Barashkov or by Bauer-Schmidt, and his collaborators do something quite similar, that they construct proxy fields kind of based on good asymptotic expansions, which in a certain sense have are martingales and therefore are good to estimate. And now we do, in a certain sense, the same thing, not in a kind of classical field theory with thermal noise, but in kind of this field theory with quenched noise. But you can play kind of a very similar you can introduce a kind of a similar idea of variance decomposition. You may think of this cutoff scale as providing a variance decomposition, and kind of work with these dynamical equations in the spirit that's done there. Okay, that's it.
People have questions or more questions?
Can one link this with the perspective of how does the environment, from the perspective of the environment is seen from the vantage point of the diffuser?
Yeah.
Diffusion in the space of landscape.
So that's the approach which I think was introduced by Tote and Valco, and then more recently used by Toninelli and Canizaro and collaborators. In order to understand this drift diffusion process, they look at kind of the generator of the environment as seen by the particle, And that generator is, has a symmetric part and a skew-symmetric part. The skew-symmetric part, in fact, is dominating, and then they do kind of a non-afraid analysis in Fock space, and they expand in Wiener chaos, and they rewrite this in terms of annihilation and creation particles. But it seems so I think by now they can also show exactly the right asymptotics for the effective diffusivity. But at least when I'm discussing with these people, I don't think that this approach yet has shown them kind of this intermittent behavior. But yeah, so the short answer, it's being done, and in fact it would be interesting to understand the connection, because that method they're using can also be used in other problems like the anisotropic KPZ equation in 2 dimensions. And so it's kind of a very flexible method, and it would be interesting if this method can be made, flexible also in these situations, right?
For some of this wisdom there.
Yeah.